Hello, physics. This is Mr. Janowski. This is the first part of the Chapter 4 slides. Chapter 4 is going to deal with linear motion and 1D kinematics. So we started off with this idea that all motion is relative. And quickly I talked about how, yes, the Earth is spinning on its axis and it's going around the sun. And the sun's going around the center of the Milky Way. And more things are happening. So there's actually lots and lots of motion going on all the time. So even if you're sitting there and you think you're sitting still in your chair, you're actually moving in a bunch of different ways. So what does it move to actually be moving? What does it mean to actually be sitting still? Well, you have to define a frame of reference. And you are sitting still in a frame of reference if your position relative to some fixed point in that frame is not changing. And you are moving if your position relative to some fixed point in that frame of reference is changing. So unless otherwise stated, the most common fixed point to use is the surface of the Earth. So unless I say otherwise, just assume that the ground is motionless. And like I covered on the second slide, that's not really true. The Earth is spinning, it's going around the sun. Lots of things are happening, but that's just what we go with. So we come to this idea of speed. So speed is any unit of distance divided by any unit of time. And I talked about how in the US, drivers like miles per hour. That's what we're used to. Most of the rest of the world would use kilometers per hour. It's a much more sensible kind of unit. Astronomers might use a different thing, like kilometers per second, light years per century, etc. In physics this year, we are going to like to use meters per second. So m divided by s, this is going to be the most common unit of speed that we will use by far. So how does speed relate to distance and time? Speed is distance over time. So if this cheetah chasing this antelope, it covers a distance of 50 meters and it takes 2 seconds to do so, its speed is 25 meters divided by 2 seconds. I'm sorry, its speed is 50 meters divided by 2 seconds, which gives you 25 meters per second, which you write as 25 m divided by s. And so here is the infamous bloody cheetah slide. So yeah, 25 meters per second. As Americans, we're not used to dealing with meters, and I don't think anyone in the world in their regular life is used to dealing with meters per second very much. So we like units of miles per hour for speed. So a quick rule of thumb is to get from a speed in units of meters per second to a speed in miles per hour is just double the number. So 25 meters per second is about 50 miles per hour. It's not super close to 50 miles per hour. It's actually closer to 56 miles per hour. But the math is easy. You just double the number, and that gets you in the ballpark. And that's how you get a sense of how fast a meters per second speed is in miles per hour. So yes, try to remember this formula. Speed is distance over time. You can always rearrange this formula and solve for either distance or time, but don't memorize those versions. So the two versions at the bottom, speed times time is distance and time is distance over speed. Please don't memorize those. Just memorize this top one. Speed is distance over time, and you derive the other ones when you need to. So then we did this thing with these three situations. If it takes Alice 1 hour to drive 65 miles, what's her speed? And the other ones. So just simple applications of this formula or a different version of this formula. So that's what we did. And quickly, yes, Alice is going 65 miles per hour. If Billy drives 55 miles per hour for an hour, how far does he go? He goes 55 miles. And finally, if Charlie drives 120 miles to get down the shore and he averages 60 miles per hour, how long does it take him? It takes him 120 miles divided by 60 miles per hour, a time of 2 hours. So, the kind of math that you're used to doing in your head from just everyday life. How long is this road trip going to take if we go at this or that speed? And how far can we go if we're going at this speed for that long? Things like that. So the difference between instantaneous speed and average speed. Instantaneous speed is the speed you are going at any particular instant. So that is what your speedometer reads. So if you're driving, you look down at your speedometer, it tells you a number. That is your instantaneous speed. So this is different than average speed. Because in real life, if you're going on a road trip, sometimes you're going to go faster, sometimes you're going to go slower. So your average speed is just your total distance over your total time. That's what average speed is. So not what your speedometer reads. And now comparing speed and velocity. So speed and velocity in regular talking are just synonyms. They mean the same thing. In physics, they have different meanings. So speed is a magnitude. whereas velocity has a magnitude and direction, which means speed is a scalar and velocity is a vector. So if you ever get a physics problem and I ask you for the speed, or I might say, give me the magnitude of the velocity, you have to give me the magnitude. So 25 meters per second is a magnitude. If I specifically ask for the velocity, you have to give me magnitude and a direction. So the flash in this case might be going 25 meters per second to the left. 25 meters per second is the magnitude. To the left is the direction. And you could also have written minus 25 meters per second, in which case I would assume you were using the convention we all use, that to the left is negative and to the right is positive. That would work just as well. So is it possible to have a constant speed but a changing velocity? The answer is yes, because velocity consists of magnitude and direction. If either one of those things is changing, then your velocity is changing. So if you're driving your car, you're on the off-ramp, so you're making a turn, even if your speedometer is pegged at a constant 30 miles per hour, because you're turning, you're constantly changing direction. Therefore, your velocity is changing. Same deal if you're skating and you go up on one blade and now you're coasting at a constant speed, but you're changing directions. So this would be a change in velocity. And if you have a beetle, the insect of a beetle sitting on a vinyl record album, as the album's going around, if the beetle just sits there on the album, it's going at a constant speed the whole time, but it will always be changing direction, so its velocity is always changing. So here are these slides comparing the things. The symbol of speed is s, its units are meters per second, and speed is a scalar, whereas the unit for velocity is v. I'm sorry, the symbol for velocity is v. Its units are meters per second, and velocity is the vector. So these ideas are very much related, but speed is the scalar version, velocity is the vector version. And then we skip this slide. Who cares about this slide? So we went from speed and velocity to distance and displacement. And just like speed is the scalar version and velocity is the vector version of the same kind of quantity, distance is the scalar version and displacement is the vector version of this type of quantity. So, for example, if Alice and Billy are standing back to back and Alice walks 10 meters east and Billy walks 10 meters west, their distances are equal. They will each have gone a distance of 10 meters, but we would say that their displacements are opposite. So if we keep with the idea that east, well, that's kind of right. We're going to say that Alice's displacement is plus 10 meters, whereas Billy's displacement is minus 10 meters because he went west or left. And similarly, if you go to a track and you run around the track, you will have gone a distance of about 1/4 of a mile. But if you come back to the starting line, exactly where you started, your displacement in that case would be 0, which seems weird and it seems unfair, but that is the difference between distance and displacement. So there are many times when you would use different symbols for these ideas, possibly D for distance, displacement, L for length, R for radius, if you were dealing with a circular kind of thing. But in general, we want to use X's and Y's. So just like this Cartesian plane that you learned in math class, if the thing is horizontal, call its displacement X. If the thing is, changing its position vertically, call its displacement Y. So X for sideways, Y for up and down. So here is the slide comparing these things. Sometimes, not always, but sometimes D for distance, which comes in units of meters, and distance is a scalar. And for displacement, use X or Y. X if it's horizontal, Y if it's vertical. The units are also meters, and displacement is a vector. So displacement is the vector version of distance. Or you could say distance is the scalar version of displacement. So these ideas are related, but they're not exactly the same thing. So what is it called when velocity changes? It is called acceleration. So this is the rate at which velocity changes. And acceleration is a vector. So acceleration is a change in velocity divided by a change in time. So I should have on here that displacement has units of meters, and velocity is the rate at which displacement changes. So velocity has units of meters per second, and acceleration is the rate at which velocity changes. So it has units of meters per second, but most people will just say meters per second squared. So displacement is where you are. Velocity is the rate with respect to time at which your displacement is changing. And acceleration is the rate with respect to time at which your velocity is changing. Or you could also say acceleration is the rate at which your displacement is changing. So that's that. And in physics class, we say acceleration, and we don't say that other word at the bottom. I'm not even going to say it. That word that starts with a D. We don't say that. Saying that word and using that word in physics class only leads to confusion. So you can say speeding up and slowing down. Those are things you're allowed to say. Those things perfect, those happen. But you have to always use the word acceleration. And never that word with the D. So, for example, if you're moving to the right and you're gaining speed, your velocity is to the right and your acceleration is to the right. Now, if you're moving to the right, but you're losing speed, you're slowing down, we would still say your velocity is to the right because your displacement is still changing to the right. But in that case, your acceleration would be to the left, which seems very weird. It seems like a bizarre way to try to say this. But trust me for now, when you're doing the physics, you have to think of it that way. And people struggle with this idea, but it's perfectly allowed to be moving in one direction and accelerating in the exact opposite direction. And that seems like a very weird way to think of it, but trust me, that's the best way to do it. So what is this symbol? Triangle. Triangle is actually a Greek letter. This is the capital Greek letter delta. So when you're doing math and physics, triangle, delta, always means change in. And we never use delta as a variable. Delta will always only mean change in. So if you want to figure out the change in anything, you take the final amount and subtract the initial amount. So delta thing is always going to be equal to thing final minus thing initial. So if I start with 8 apples and I end up with 5 apples, what is my delta apples? So delta apples is equal to apples final minus apples initial. So 5 apples minus 8 apples. And you get minus 3 apples is delta apples. And the minus would be important in this case. You will goof with the math if you try to plug in plus 3 apples and if this were part of a problem. So we write A is equal to delta V over delta T because it's much easier and quicker to write that than it is to write out the words acceleration is equal to change in velocity divided by change in time. So delta V is change in V. So V final minus V initial, but that takes too long. So sometimes you would write V sub F minus V sub I. And this is all divided by delta T, which is T final minus T initial, or T sub F minus T sub I. So if you're mathematically inclined, you're probably looking at this and thinking, okay, and maybe this math and this algebra is kind of annoying you. Don't worry. Once you start doing it, it becomes more natural. So the example we did was at time t equals 0, I'm traveling 8 meters per second to the right. And at time t equals 2 seconds, I'm traveling 14 meters per second to the right. So what is my acceleration? So we have to figure out what t initial and t final are and what v initial and v final are. So t initial, our initial time is 0 seconds. T final, so when do we stop the situation? Well, that's 2 seconds. V initial, how fast were we going at the beginning of this situation? So we were going 8 meters per second. And at the end of the situation, we were going 14 meters per second. So that is V final. So if we want to figure out the acceleration, start up here with the definition of acceleration. Sub in V sub F minus V sub I for delta V. Sub in T sub F minus T sub I for delta T. Plug in your numbers everywhere. Do your algebra correctly. PEMDAS. Respect your parentheses. And you're going to end up with 6 meters per second divided by 2 seconds. And if you ask your calculator what's 6 divided by 2, you end up with 3. And your units would be meters per second squared, which are the units of acceleration. So we're very happy about that. So here is the slide like this. So our quantity is acceleration. Its symbol is A, which makes perfect sense, A for acceleration. Its units are meters per second squared, m divided by s squared, and it is a vector. And I said this in class, for whatever reason, there's not a word for the scalar version of acceleration. So the scalar version of displacement is distance. The scalar version of velocity is speed. And the scalar version of acceleration, well, there's not a word for it. I don't know why. It seems very incomplete. These kinds of things bother me. So again, because acceleration is a change in velocity, and velocity has both speed and direction, if either speed or direction is changing, that is acceleration. And if both is changing, well, that is definitely acceleration. So car-based examples of a car that is accelerating. So if you are at a stop sign and you look left, look right, look left, and then you step on the gas, so you're gaining speed in a straight line. Well, gaining speed, that's acceleration. Everyone accepts that right away. They're familiar with that use of acceleration. The thing that people struggle with when they first start taking physics is now that your car is coming to the next stop sign and you start hitting the brakes and you start losing speed. In physics, we still call that acceleration. We just call it acceleration in the other direction. So if you're driving east and you're coming to a stop sign and you hit the brakes, we would say your velocity is to the east because you're moving to the east, but your acceleration is to the west because you were slowing down to the east. I know it sounds very bizarre at this point, but trust me, this is how you do it. And acceleration, that is a change in direction. So if your car is maintaining a constant speed of 30 miles per hour and you're making the turn around an off-ramp, you're changing direction. So that is acceleration. And if your car is speeding up or slowing down as you're doing the off-ramp, so at this point you are changing your speed and you are changing your direction, well, that is definitely acceleration. So I skipped over these slides real quick. These slides, I'll do this one. It's just useful to see all of these things together and compare them. And maybe this might help build the idea in your head of what each of these things are. So displacement is where the object is. Its symbol will be X or Y, depending on if it's horizontal or vertical. And its units will be meters. So velocity is the rate with respect to time at which displacement is changing. So velocity is going to have the units of displacement divided by time. So meters divided by seconds, meters per second. And acceleration is the rate at which velocity is changing. So it will have the units of velocity divided by time. So the units of velocity are meters per second, divide that by seconds, and you end up with meters per second squared. So if you happen to be taking the calculus now, you would say that, okay, displacement, we'll call that one x. Let's just deal with horizontal. So velocity, that would be the first derivative with respect to time of displacement. And acceleration would be the second derivative with respect to time of displacement. Or you could say it's the first derivative with respect to time of velocity. So yeah, just to compare this to what Mr. Babias is teaching you, that's how it works. Now, if you're not taking calculus and calculus is either in your future or maybe you're going to avoid it like the plague, don't worry. This is not a calculus-based physics course. But yeah, that's what these ideas are. I know that Mr. Babias does problems involving these exact things: displacement, velocity, and acceleration. So definitely ignore this slide. This slide is just me being goofy. And this is all completely accurate, but I said the things in unusual ways. Acceleration is the rate at which where the object is changing. Ignore it. So then we talked about motion maps and the red and the blue car. So the idea with this slide is both cars are going down the road, and they are both leaking oil at the same constant rate. So you can see oil dripping out of the car. So maybe 1 drop per second, or maybe some faster rate than that, but they're both, dripping oil at the same rate. So the thing is, the cars went left to right, but you weren't actually there to see them. So you didn't see the cars moving by. You came by later, and you saw the oil drops on the road. So by looking at these oil drops, can you figure out how are the cars moving? And the red car is this one on the top, the blue car is here on the bottom. And hopefully you can figure out that the blue car on the bottom, well, it was moving faster. How do you know it was moving faster? Because the dots were further apart. So you know the blue car was moving faster because the dots are further apart. You also know that both cars, the red one going slower, the blue car going faster, both cars were keeping constant speeds. And the way you can tell that is the dots are all evenly spaced. So on a motion map, so these are like the questions we did on that annoying assessment on the second day of class. On a motion map, the location of the drops shows you the displacement of the car. The spacing between the drops gives you the velocity. So that's motion map. And a slightly trickier example, again, red and blue car, both are leaking oil at a constant rate. You're not there to see them go by, but you come along later and you see these oil paths. are these patterns of oil dots. So by figuring these out, again, red was on the top, blue was on the bottom. What do you know about how these cars were moving? Well, you can tell that the cars were accelerating. The red car started at rest and gained speed moving to the right. So originally, when it was moving slowly, the dots are very close together. But as it's gaining speed, the dots are getting further and further apart. The blue car on the bottom, well, at the start of this thing, the blue car was already moving. It was moving kind of fast to the right, but it was slowing down. So that's why the dots are getting closer and closer together. So again, with a motion map, we just covered that the location of the dots shows you the displacement. The spacing between the dots shows you the velocity. And how the spacing between the dots changes, that's how you know what the acceleration is. So that's that. So quickly to review, how fast is 40 meters per second in miles per hour approximately? Well, we have a way of remembering this. We use the bloody cheetah. So you just double the number in meters per second, and it gets you out to 80 miles per hour. So what is the difference between speed and velocity? They're both related, but speed is the scalar. It only has magnitude, and velocity is the vector. It has magnitude and direction. So what is the formula for velocity? Well, speed is distance over time. Velocity is also distance over time. It's the vector version of it. And yeah, what are the units for velocity? The units for velocity in physics, we are going to use meters per second, m divided by s. And then 3 more ones real quick. So when we're doing the motion maps with the cars, the location of the drops gives you the displacement. The spacing between the drops gives you the velocity. And how the spacing between the drops changes, that gives you the acceleration. So yeah, that was a lot for this video, and we covered a lot in class at a breakneck speed, and I kept apologizing, and I'll apologize again for that. But we really had a lot to cover to get all this stuff, under our belts, so that we can start doing other things. So hopefully you found this helpful.